Here I have a polynomial function, and if I asked you to find the absolute maximum, you should key in on the point that's up here. When I look at that point compared to any of the other points on the graph, it is the very highest point. Its y value is bigger than any others. Now, that's not to say that it is not a relative extrema also, because it's a critical point and it's higher than the things nearby. So this particular point is an absolute maximum and also a relative maximum. Compare that to the point right here, which is higher than the points nearby, so it's a relative maximum, but it is not the absolute maximum because there are points on the graph, such as the ones up here, that are even higher. This has a relative minimum right about there, because that point is lower than the ones nearby, but there is no absolute minimum because this graph continues to go down, down, and down, and down, down, and down on either one of the sides. So in this example, we can have an absolute maximum, but not an absolute minimum. Now here's a parabola with exactly the opposite. Down here at the bottom, at the vertex, is a point that is lower than any other point on the graph. That means that it's an absolute minimum. But because on the ends the graph continues to go up, there's no absolute maximum. Any value that you might try to give me, I could probably pick something farther to the right or farther to the left that is even higher. So that motivates the following definition. Let f be a function defined on some interval, and let c be a number in that interval. Then f of c is the absolute maximum of f on the interval if every point in that interval, when you put it into the function and get f of x, it's going to be less than or equal to the y value at that point c. So this says that the y value at c is bigger than any other y value in the interval. Now, f of c is an absolute minimum of f on the interval if all the points on the graph in that interval are bigger than the y values at c. So this is saying basically that f of c is smaller than any other y value, and an absolute maximum says f of c is bigger than any other y value in the interval. Here's an example where I've got an interval that extends from an x value right about there to an x value here. If I want to find the absolute maximum here, I'm going to find the portion of the graph that's higher than any other. So right here, I see an absolute maximum. If I'm looking for the absolute minimum, I want to find the place on the graph where the y value is the very smallest, and that's down here. So this place would be an absolute minimum. We also have some relative maxes and relative mins. There's a relative min right here. The absolute min is also a relative min, and we have a relative max at this bump right here. But when we talk about absolute, we're talking about the very highest or the very lowest, and the way we distinguish that is by looking at the y values. Now here's another example. On this section of graph, there are no bumps or dips, so there's no relative max or min. But there is an absolute max because there's a point here that's higher than any other. There's also an absolute min because there's a point here that's lower than any other. But again, there's no relative max or min because there are no critical points along this graph. Now in this example, we're defined from an x value right about here over to here, and if I want to find the very highest point, it's right there, and it occurs at a critical point that is in fact also a relative maximum. But for our purposes, this is an absolute maximum. If I'm looking for the absolute minimum, that's at the point down here. It's lower than any other. Now what you're probably starting to notice is that when you have a very highest point or a very lowest point or an extreme value, that our extreme values are occurring in certain places. They're usually occurring on the endpoints or at a critical point. What you should have also noticed is that for all of these functions that I just showed you, they were continuous, which means I could draw them without lifting up my marker, and they were on a closed interval. They included their endpoints. And in every one of those three examples, we had an absolute maximum and we also had an absolute minimum. They were guaranteed. If I did not have a closed interval or I did not have a continuous function, I wouldn't be guaranteed an extreme value. For instance, here's a function that's defined from an x value here to an x value there. Since it includes the endpoints, this is a closed interval, but it's discontinuous because it has a vertical asymptote. What you're going to notice right away is because the graph shoots up along the vertical asymptote, this has no absolute maximum. It does have an absolute minimum at one of these endpoints, but it doesn't have a maximum. So as soon as we take out this idea that we need a continuous function, suddenly the graph can shoot upwards and we're not guaranteed both extreme values, that is, an absolute max and an absolute min. Here's an example of a function that's continuous. I can draw it without lifting up my marker, but it's not on a closed interval because it doesn't include this endpoint. Now if I asked you to find the absolute minimum, you'd clearly say that down here on the left-hand side at -3, -2, that is an absolute minimum. But now what if I ask you about an absolute maximum? Some of you might look and say, oh, well that's at 2, 3 right here. But the problem is that point's not included because of the open circle, because it's a partially open interval. Well, then the next question is, well, then it must be right here just next to it. So let's say at about 1.9. But if you say that the maximum's at 1.9, I'm going to look at it and say, well, I can go to 1.99 and it's going to be slightly higher. Or 1.999 and it's going to be slightly higher. In fact, for every value that you give me and say, oh, I know what the maximum is, I'm going to move slightly closer to 2, and I can always do that, and give you a place that's slightly higher. Because of this, there is no absolute maximum. It looks like there should be, but we can get infinitely close to that point that's not included and still not reach the maximum, because the closer we get, the higher up we get. So that's why we need closed intervals here. Because of that problem, as we get closer and closer to an open endpoint.